Let's move on and turn to the final design that we're going to review, the case control study design. In this type of study, the investigator identifies cases, and these are individuals with the health outcome of interest, and controls, individuals without the health outcome of interest, and compares the two groups with respect to an exposure or a risk factor that's under study. So the case control design requires a number of assumptions that must be considered when designing and conducting the study. First, cases included in the study should be representative of all cases of disease, and both the cases and the controls should be drawn from the same population so that the controls are susceptible to developing the disease. That is, the controls should have the potential to have developed the disease, they just didn't because of some other factor or the exposure that you're going to study. Finally, similar to a cohort study, the exposure data that you collect for both the cases and the controls needs to be available for both groups, and it has to be measured in the same fashion so you don't introduce bias into your study. Graphically, we can think of a case control study as starting in the present with the selection of the cases from the population of all individuals with the disease and the selection of controls from the population of all individuals without the disease. After we've identified and enrolled the cases and their controls, we look to the past to characterize the exposure for each group. In this case, we identify the number of cases with and without the exposure and the number of controls that did or did not experience the exposure. The odds of being exposed among the cases is calculated, and the odds of being exposed among the controls is calculated. And the ratio of these two odds, the odds of exposure among the cases and the odds of exposure among the controls, the ratio of those two is the odds ratio that's calculated as the measure of association in a case control study. As we just discussed, the analysis of a case control study includes the calculation of the odds ratio. So remember that odds are defined as the probability that an event will occur divided by the probability that the event will not occur. So in the case control scenario, the odds ratio is the odds of exposure among the cases compared to the odds of exposure among the controls. So this differs fundamentally from a relative risk that we calculated in a cohort study, where in that case the rate of disease development among those that are exposed and those that are unexposed are observed. So these rates are compared. In the case control design, we've already defined the outcome of interest, and we're looking backwards, retrospectively, to calculate the odds that the cases that we've identified were exposed compared to the odds that the controls we've identified have been exposed. So turning now to our familiar 2x2 table, the odds of exposure among the cases is the number of exposed cases compared to the number of non-exposed cases, and the odds of exposure among the controls is the number of exposed controls over the number of non-exposed controls. So here the odds of exposure among cases is A divided by C. The odds of exposure among controls is B divided by D. And so the odds ratio is calculated as A over C divided by B over D, which is equivalent to the familiar cross-product formula that you've seen for the odds ratio, A times D divided by B times C. There are a few variations of case control designs that are important to keep in mind. So the first one is a nested case control design where the cases and the controls are selected from a well-defined cohort. And the controls here in this design are selected from a random sample of individuals in the same cohort at the time of each case. So that's important. So cases are compared with a sample of at-risk cohort members at the time when the case occurred. So this design allows for cases that occur later in the longitudinal follow-up of the cohort to actually serve as controls for cases that may have occurred earlier in the cohort's observation period. The nested case control design differs from the case cohort design in that the case cohort design allows for controls to be selected as a random sample of the total cohort at the baseline. So in this design, the case cohort design, a sample of the entire baseline cohort can serve as a control group for multiple sets of cases in the same cohort. So both the case cohort and the nested case control design are conducted within a cohort study. The difference is the selection of the controls from the cohort as a whole. Another variation of the case control study that I use frequently is the case crossover design. This design is appropriate when the risk of an outcome is increased for a brief time period following an exposure. So a good example of this is air pollution, where the risk for an acute health event is elevated for a short period following times of elevated exposure. So in this case crossover design, cases serve as their own control and the exposure is assessed during the time immediately preceding the case period. The control periods are selected from times where the disease outcome or the acute health effect is not taking place, and the exposure that immediately precedes those control periods is also assessed. So you're measuring exposure immediately preceding the case period and immediately preceding the control periods, and you're comparing the exposures during the case period and the control period. The benefit of this design is that each case serves as their own control, so confounding and bias due to personal characteristics or poorly selected controls is eliminated due to the design of the study. The study also offers increased power to detect associations. Case control studies offer the advantage of being less time-consuming and less expensive than cohort studies. And in addition to this, in the case of rare outcomes, a case control study design is actually preferred. There are some important disadvantages to the design, though, that should be considered. First, the measure of the association in case control studies is the odds ratio, which does not directly estimate risk. In addition, while case control studies are preferred when studying rare outcomes, the design really isn't suitable for studying rare exposures. You also have to carefully consider sources of bias when you're designing and conducting your case control studies. Two of the most common sources of bias in the design include selection bias, due to differences in the characteristics between those you selected for inclusion in your study and those that you did not include or select for your study, and recall bias, which is the systematic error due to differences in accuracy and completeness of recall of past exposures. So for example, the most common cause of recall bias in a cohort or in a case control study are cases remembering or recalling more often past exposures than controls. Matching is often done in case control studies in order to make the cases and controls more comparable with respect to some potential confounding variables. So for example, you may want to select your cases and controls such that they are similar with respect to age, race, or gender, and therefore you won't need to worry about confounding due to these variables in your analyses. You can also increase your sample size and power by selecting multiple matched controls per case in your study. So there's a number of ways to conduct matching in your studies. Two of the most common are individual and frequency matching. Individual matching is when the investigator selects one or more controls for each case that they've enrolled in the study, and they do this individually based on the desired matching characteristics. So they might match on age or race, and so for every case of a certain age and race, they select a control with that same characteristic, age and race. Frequency matching is conducted by selecting the control group overall to balance the overall frequency and distribution of the matched variables between the cases and controls. So in both techniques, the idea is to get a match between the cases and controls with respect to some of these potential confounders, including most frequently age, race, and gender. So what are the advantages and disadvantages of matching? Well, matching does control for confounding and it tends to increase statistical power. However, keep in mind there are some potential difficulties in finding appropriately matched controls, and this is especially true when you start to match on multiple variables. Another disadvantage of matching is that you're not going to be able to assess any associations between any variable you've matched on and the outcome of your study. So this might be okay, and in fact it's preferred when you want to make sure that you don't have any confounding due to your matched variables. However, keep in mind you're not going to be able to assess any interaction in a matched case control study between any variable that you've matched on and the exposure of interest. So to conclude, keep in mind that there may be multiple designs and ways to conduct your study, but your goal is to pair the best data with the best design so that your estimates of association are valid. This is a nice figure of some factors to consider when choosing your study design, but remember that choosing a design is an art and likely going to be a fluid process. So good luck, and I'm happy to help you work through the process as you get started.